Introduction to Statistical Learning, Chapter 11, discussing survival analysis, and we're in the conceptual questions, question number 8, which is right here. So we're given the survival function and the hazard function and the density function in the book. These equations right here, 11.2, 11.9, 11.1 respectively, and then I've reproduced them down here in the answers part. We're supposed to, and I guess we have one more, which is that capital F of t is 1 minus the survival function, but in probability usually this is, well, I shouldn't say usually because these are all equivalent, but we often think about F of t as the cumulative distribution, which is just the integration of the density function right here. And so by extension, 1 minus s of t is the same as the integral of the density function. Okay. And we're supposed to show the two following relationships. The density function is equal to the cumulative distribution function of f of t, but that's kind of how it's defined, so we're going to take a trickier route in defining that. And also that the survival function is the integral of the hazard function from 0 to t, then raised to the, as a power of the e, of the constant e. And I should say that integral is negative. Okay. Saying math is much worse than just looking at math, so I apologize if that was confusing. Okay, so here I give the different expressions. So 11.2 defines the survival function. Okay, it's just the probability that the time of an event is greater than some arbitrary time, little t. So the time of the big event is big T, and then little t is some arbitrary time. The hazard function is given as a limit, so it's kind of like a derivative, but it is the probability that an event occurs after little t, but before or at little t plus some delta t, given that we've already survived past little t, and then divided by delta t. Okay, but that top part I think gives you most of the intuition. It's the probability of some event happening within some discrete interval, given that we've already passed, the bottom edge of that interval. Now the book also gives the hazard function as this guy right here. Okay, and we'll actually kind of come to this. But we won't start with this assumption to derive the two relationships because it's too easy basically. and the question is asking us to use these equations here. Okay, and finally the density function. It's the instantaneous rate of death at any given time t. But similarly, if we look at that, again, it's a derivative. What is a derivative of? It's actually a derivative of the cumulative distribution. But it is the probability of an event happening within some interval. Okay, so let's first show this first relationship, that the density function is the derivative of the cumulative function. Okay, and we're not just going to use that fact about calculus or probability to do it. So we'll take a little bit more circuitous route using the definitions that were provided for us up here. Okay, so there's a few ways you could do this, I'm sure, but we'll just start with the definition of capital F of t. Okay, and it's 1 minus s of t, which means 1 minus the probability that the event happens after some given interval. Okay, and this expression right here, right there, can just be written as the probability that it's hard to highlight these things, that the event happens before or at time little t. Okay, sometimes these little conversions of removing negative signs and then flipping the greater than equal to, you have to actually do it on paper sometimes. Even though it's a very basic thing, sometimes it's just hard to keep track of everything. But So, so we have that f of t actually equals this right here. And if you're familiar with cumulative probability distributions, that should just, make complete intuitive sense. And so now if we take the derivative of that, because ultimately we want to, we want to show that f of t is the derivative of that. So if we take the derivative of that in terms of the limit definition of derivatives, so I won't review that right here, but hopefully this looks familiar. Okay, so we take the limit of capital F of t plus delta t minus f of t, and then just allow delta t to go to 0. Okay, and if you just churn through this setup right here, you just come to this derivative right here, which is the same as f of t. Okay, so again, I think it's best if you actually kind of walk yourself through it. Speaking math is much harder than just showing math. Okay, and so now we'll show this second relationship, that the survival function is the exponentiation of the negative integral of the hazard function from time 0 to t. So let's come down here. So this is a little bit longer, and I've kind of broken it up into 3 little chunks here. Okay. Okay, so the first thing that we do is we just write the hazard function. Okay. And then it's just a function of, or it's just a process of simplifying, in a directed manner. So for instance, the first simplification that we make here, so up here we have this conditional probability that t happens within the interval t and t delta t, given that big T happens after little t. Okay. Well, we can rewrite conditional probabilities by saying the probability of event A and event B divided by probability of event B. So that's just normal conditional probabilities. We have that here. Okay. Well, now this very tippy top term, right? The intersection, the and statement. Well, that can be simplified because this second statement is already encapsulated in the first statement. Okay, so you really need to verify that for yourself. But the lesson there is that we can simplify that term even more. Okay, so we've simplified that term. All right. Now, so this is the probability. It's so how do I want to say this? So now we can drop this survival function. We could put it down here in the denominator, but because it doesn't have a delta t in it, we can take it outside of the limit. Okay, and so now our expression becomes this. Now we've already seen that that this expression, the thing that we're taking the limit of, well, when we take the limit of it, is just the density function f of t. And so all of this simplifies to f of t over s of t. And then we've already shown that little f of t is the derivative of big F of t. Okay, and so now we have this expression. All right. Well, big F of t is just 1 minus the survival function. Okay, and so now we have all of this. We're taking the derivative of 1 minus the survival function. And when you take that derivative, you just get the negative of the survival function. And this is the only part I don't like about some of these things, and I feel ashamed for doing it myself, but I couldn't think of a better way. But this is just one of those derivatives that you learn to recognize. So it turns out that this right here is the derivative of the natural log of the survival function. Okay, if you go ahead and convince yourself of that. But if you were to take this derivative, you would get this guy right here. So it's not fun doing it that way, but there you go. Okay, so now we need another step here, or we're getting out of this workflow and moving to a different chunk. Okay, so we've shown that. So in this first part, we've shown that the hazard function is this guy right here. Okay, and so now if we were to integrate both sides from 0 to t. Okay. So when we do that, we introduce the dummy variable u, so that's why u has replaced t here. When we do that, you can just churn through this integral until you get here. Okay, so I I won't go through every step there for you. Well, there's one step actually we're showing. So we go through this. So we're just kind of looking at the right-hand side here. We already know what this derivative is because we already saw it above. So we have this. This integral is this. Okay. So if I distribute the negative sign, then I have s natural log of s of 0 minus natural log of s of t. Well, what is the survival function at time 0? Well, here we're assuming that everybody was alive at the beginning of the study. So that's 1. So now I have the natural log of 1. That becomes 0. And then we have, so that just simplifies to this, this integral being equal to the negative natural log of the survival function at time little t. Okay, right? And so now we can set this and this, and this equal to one another down here, which we do. And then to get it outside, to no longer have it as a natural log of the survival function, we exponentiate both sides and we get this, and that's the relationship that we were meant to show in the beginning, wherever it is, way up here. Okay, so so I hope that was helpful. If anybody has a more intuitive way of doing that, then please let me know.